Hello guys. So we continue our discussion of wave optics, and as a reminder, last time we considered Young's double slit experiment, and considered which actually allows to realize experiments with interference of light originated from two coherent sources. So we considered different conditions for constructive and destructive interference, assuming the difference in path or from the point where we observe the interference effect towards the coherent sources of light. And also we considered the quantitative description of light intensity distribution, because these conditions for destructive and constructive interference, in particular the angular and linear position of interference maxima and minima, they give us their position only the center of these bright and dark fringes, maxima and minima respectively. However, if we want to know the light distribution, so we need to proceed further and calculate this distribution of light intensity along the screen where this interference image is projected. So we have done that and have shown that with the increase, so for two-slit interference, there is some cosine square dependence of position along the screen. So the light intensity goes from 0 to some maximum. So we have certain gradient of light intensity from dark to bright, and then from bright to dark. So that repeats along the screen. So now we proceed further, and we're going to consider in details the interference effects caused by reflection. So when we have some thin film on certain medium, and because of such optical system, we also in the reflected light can also see interference effects. So before we proceed to this particular case, it is necessary to consider change of phase of light reflected from more so-called more optically dense material than the medium in which originally the electromagnetic wave is spreading. So more optically dense means that the second medium from the interface between first and second medium reflection is going to happen, will possess higher refractive index than the first medium. So there is certain effect which should be taken into account when we deal with interference pattern formed by the reflection of light. Okay, let me change the screen. And we consider such a system. So let's say we have some mirror surface which reflects light very well. And we have some point, some object. Then this part, we have the screen where this interference will be observed. So let's consider one beam directly going from the object towards the screen, and here we have some point P, and another will be going downwards, then reflected from this mirror, and will also come to this point P. So if we consider the reflected beam, it will appear like originating from another point, let's call it S prime, and the distance between this real object and its kind of image will be some d. So in this case, we can consider this S and S prime as double slit, like two coherent sources of light, and interaction between these beams originated from S and S prime will result in some interference pattern. And what is interesting that if we stick to such a model, the condition for interference maximum, like constructive and destructive interference conditions, they are different. So they, if we previously derived these conditions for constructive and destructive interference as d times sinus theta equals to m lambda, and then, so this is for constructive interference when m is equal to 0, plus minus 1, plus minus 2. Then for destructive interference, d sinus theta is equal to m plus 1/2 times lambda, where m is the same as for the previous condition. So these are conditions for constructive and destructive interference, but for the case when reflection is involved, and assume that here we have air or vacuum, n is equal to unity, obviously this n, let's say n1, n2 is larger than n1, because we know that index of refraction is equal to unity only for vacuum, and then like free space, and then for any other material, it will be higher. So the conditions for destructive and constructive interference, they are swapped. So we just change these conditions, and that happens because the phase of electromagnetic wave, which is reflected from medium with a higher index of refraction than the one in which the wave is traveling. So it's particular this case. We have some medium like vacuum in which wave is traveling from this source towards the interface. It's equal to unity, then n2 is larger than n1, and means that we have reflection from the medium with a higher index of refraction. So in this case, the phase is changing by 180 degrees. So, and that is the reason why conditions for constructive and destructive interference are changing in comparison to two real sources of coherent light, coherent electromagnetic radiation. So this fact should be taken into account when we deal with some interference effects involved, which involve reflection from different interfaces. So should be mentioned that this is happening only when N2 is larger than N1, and if there is a situation in the contrary, N1 is larger than N2, this phase change in 180 degrees doesn't happen. So this can be shown from Maxwell equations, but definitely goes beyond the scope of our course. However, we need to take this fact into account when analyze in future some interference effects involving reflection. So since we already have established this concept and this fact, then we can proceed further and consider interference effects in thin films. So interference effects are commonly observed in thin films. For instance, a thin layer of oil or gas on water. So that is quite common picture when there is some spill of gasoline on water. Gasoline is lighter, so it forms a very, and it's not mixing with water, so it forms a very thin layer on top of water. These are two different mediums with two different index of refraction, and that is the reason why such a system, such optical system can result in different colors. Excuse me, please. I'm sorry about that. Okay. So such an optical system can result in the interference effects, which we see in the form of some colorful lines. That is happening because we don't have monochromatic source of light, but sunlight consists of different wavelengths, and different wavelengths appear in interference pattern, which is shifted from its position, depends on the wavelengths of the part of the solar spectrum. So in order to consider quantitatively this effect, we consider a film of a uniform thickness, T. So this is film thickness T, and index of refraction, which we assume to be N. So the wavelengths of light, we consider some monochromatic light, and lambda n is the wavelength inside the material. So we remember that by changing the when the wavelength is electromagnetic wave is going inside the material, its wavelength is changing accordingly to the value of its refractive index. So we discussed this previously. Then we have such a system which is our thin film N, and we have air, for instance, from both sides of this film. So it will be N equal to 1, N equal to 1. And here it just gets some value, depends on the material of the thin film which we consider. So this is our thickness, T. And maybe I will extend it towards here so we have more space for drawing. So this lambda n is lambda divided by index of refraction of this film, and lambda is the wavelength in air or free space. So let us see what happens with light, how it is reflected and refracted in such a system. So we go here. This is our incident light. Part of this light is reflected. It's beam number 1, let's consider. Then part of it is refracted. So it goes into the film. Then it is refracted second time at the opposite interface. But also part of it is reflected from the opposite interface, like this. And then it's refracted again. And this refracted light is coming out in the same direction as the first reflected light. So this is beam number 2. So if we assume very small incident angle, theta, then what we get that this extra distance which second beam is traveling in the film will be in first approximation defined as 2 times t. So it goes once down and once up. So if this angle theta is small, then we have something like this. It goes down and goes up. So this total difference in path will be 2 times t. So another thing what we should keep in mind here, that this first wave, which is like beam reflected from the interface air film, here we have condition where the medium from which this light is reflected possesses a larger index of refraction, and that's why we have this 180 degrees phase shift, which we should take into account. However, the second, like light in the second beam, is reflected here at the interface film air, and means that the interface from which this light is reflected possesses smaller index of refraction than the medium in which the beam was originally traveling. That means that this change in phase of 180 degrees doesn't happen. So this should be taken into account. And now we need to set the condition. So we know that now for constructive interference, taking into account this 180 degrees phase shift, the condition for constructive interference should be this difference in path, which is 2t, 2 times t, should be equal to the half, like to the multiple number of half of wavelengths. So we can set this condition lambda n, wavelengths in the material of the film, divided by 2. So if we want to set in general condition, so we need to put this m plus 1 divided by 2. So let us write down this on the next slide. So the condition for constructive interference of this first and second beam, which we considered, will be 2t times m plus 1/2 lambda n, where m is equal to 0, 1, 2, and so on. So this condition, I want to underline, takes into account that we have this delta phi phase shift of the reflected light in the beam number 1, which is 180 degrees. Otherwise, the condition for constructive interference would be just m times lambda n. Now we need to remind that need to recall that lambda n is equal to lambda divided by n. N is refractive index of the material of the film. And eventually we can write the following for the constructive interference conditions: 2 times n times t. So if we substitute instead of lambda n, its expression of in terms of lambda and n is equal to m plus 1/2 times lambda. So the general condition for the destructive interference obviously will be if in this difference in path we can fit some number of full wavelengths, not some number of half wavelengths. So in this case, for destructive interference condition, we can write 2 times n times t is equal to m times lambda, where for both cases, m is equal to 0, 1, 2, and so on. So another thing what should be highlighted here, that this rule for the conditions for constructive and destructive interference, which we introduce here, they will be true only in certain conditions. For instance, when we have this film in air environment, when we have air from one side and air from other side. If, for instance, we have air from one side, then we have this film. Let's say here is air, n is equal to unity. Then we have some film with, let's say, n1 refractive index. And then we have some different environment, not air, with N2. So if N2 is larger than N1, this will be a different optical system, because this light, which is reflected now from the interface film new environment, will also change in phase by 180 degrees. This fact means that the net change of phase of light in the beam 1 and light in the beam 2 will be equal to 0, because this one changes by 180 degrees and this one changes by 180 degrees. Then net change in phase because of reflection is equal to 0, and conditions for the constructive and destructive interference will also swap again. So this fact also has to be taken into account, and be very careful when you deal with some problems. Be careful with the conditions and the relative like ratio of refractive indexes of different mediums. So another option for forming interference effects involving reflection is so-called Newton rings. And maybe I can share now my screen. So here you see the system which allows to measure this refraction, this interference effect. So if we have a glass substrate and planar convex lens on top of it, then what happens? If a different distance from the center of this lens, which is in contact with the glass, so there is no gap, like air gap between glass and lens. If we go from this center further to the edge of the lens, this gap is increasing from 0 to some maximum value. So then what happens if some light comes to this system? So part is reflected, is like this beam 2 from the interface between lens and air. And the second is going inside air and comes back because of reflection from the glass surface. So when these two beams come to the observer, they cause interference effect. Since we have at different points, different distance between, like different thickness of this air gap between the lens, we will observe at different distances from the center maxima or minima for interference effect. Depends on the gap, on the wavelengths, of course, of this light, and on the gap between lens and the glass substrate. So this interference picture looks like some circles, dark and bright circles, which correspond to minima and interference, constructive interference and destructive interference. And usually this approach, this effect, is used for checking the quality of optical lenses, since it is very sensitive technique which will take into account very small deviations from the ideal curvature, like desired curvature, if it's not smooth and right uniform curvature of the lens, then these circles will not look like circles, but they will have some deviations from right circles, and also will have some local disturbance. So that will show that the quality of the lens is not good enough, and that requires additional polishing and treatment in order to make it of high quality. So another thing what I would like to discuss now is some application, practical application of these interference effects in thin films. Let me stop sharing this. Sometimes it is necessary to reduce amount of light which is reflected from the surface. So this could be necessary, first of all, as these are called anti-reflective coatings, and they found their application first in some optical systems, in binoculars and telescopes, when you want to collect as much light as possible without losing light for reflection from your lenses. So these lenses were covered by thin films in order to reduce reflection at certain wavelengths, or if you have a complex system of different thin films, you could reduce reflection in a wide spectral range. Means that, let's say, cover all visible range. That is perfect to improve the quality of images in optical instruments. However, this is not the only application of anti-reflective coatings, but also in photovoltaic devices, so-called solar cells. We also want to absorb in active layer, which converts light into electricity, as much light as possible. So we want to reduce losses because of reflection. So for instance, if we consider such a system, like some silicon solar cell, the most common one. So this is our silicon. And let's say here is some silicon oxide layer on top of this silicon. Then we have here air with n equal to unity. Then we have n of silicon monoxide 1.45, and n of silicon is something 3.5. So let's see what is going on when light is hitting this sandwich. So as we considered earlier, we have like incident light and reflected light from the first interface, which we call beam 1. Then refraction, reflection from interface silicon oxide silicon, and we get another refraction and beam number 2. And some refraction here. Light is going inside silicon substrate where it is fully absorbed. So since these two refractions happen from the interface with larger n than that of the medium where the light was traveling, there is in both cases phase shift of 180 degrees. Means that the net phase shift is equal to 0. So the condition for interference, destructive interference, which we want in this case, because if we have destructive interference of these two beams, they will cancel each other, compensate each other, and that means that the reflected beam from the surface will be with smaller intensity. Ideally, it will be just equal to 0. There will be no reflection from the surface of this sandwich because of destructive interference of these two beams. So we want for anti-reflective coatings have this destructive interference condition. And since we have for both cases phase shift of 180 degrees because of reflection, there is net zero net phase shift, and the condition for destructive interference will be 2 times n times t. So t is the thickness of this anti-reflective coating, equals to lambda divided by 2. So now we need to decide which wavelengths we want to pick up. And if we consider solar spectrum distribution, solar light spectral distribution, we will see that maximum is somewhere close to 550 nanometers. It's green light, and kind of makes sense that if you have option to make only one layer anti-reflecting coating, we would like to reflect to reduce reflection of that wavelength, which brings us maximum energy from the solar spectrum. So let us consider this particular wavelength will be 550 nanometers. And now it will be a question, let's say, what thickness of this silicon monoxide layer on top of silicon solar cell we need in order to realize this anti-reflective coating. So that answer can be obtained from this condition for destructive interference in this system, and this thickness would be lambda divided by 4 times n. And if we substitute here this numerical numbers, like values, 550 nanometers divided by 4 times n is refractive index of refraction of this silicon monoxide, 1.45. And that will give us like something around 95 nanometers. So that is the required thickness of this film. In this particular optical system, because obviously we have some different material for anti-reflecting coating and a different semiconductor from which this solar cell is made, they will possess different values of index of refraction, and that's why the thickness will change. Also, the thickness will be different if we want to realize this anti-reflecting coating for different wavelengths. But for this particular combination, we require thickness of 95 nanometers. So one more thing we want to discuss is the Microsome interferometer. Let me share my screen again. And yeah, here we have this schematics of Microsome interferometer. It consists of light source, which usually Microsome interferometer nowadays is used to measure distances with the most, like with the highest, most accurate and precise way. For that, usually light source is monochromatic light source, like some laser with well-known wavelengths of the emitted electromagnetic waves. So that is a critical requirement. You need to know the wavelengths with a high precision. Then this laser beam reaches the beam splitter, so-called. It's semi-transparent mirror. So part of this beam is reflected, like half of its intensity is reflected towards mirror M1, and another half just transmits through the semi-transparent mirror, the beam splitter, and travels to mirror M2. This M1 and M2 mirrors, they are oriented along the lines which are perpendicular to each other. So these mirrors M1 and M2, they are like 100% reflective mirrors, like close to 100%, but like fully reflective mirrors. And all light which hits this mirror M1 and M2 is reflected backwards. Then these beams, which are like two beams, they are coherent because they were splitted from the same beam generated by laser. Means coherent means that there is constant phase shift between them. They meet at this semi-transparent beam splitter back, and observer, with the help of some optical instrument, telescope, usually some CCD camera as a detector, not just with eye, observe some interference picture originated from the interference between these two reflected beams from mirror 1 and mirror 2. So obviously that the difference in path will be the difference in the distance from this beam splitter to mirror M1 and to mirror M2. So by changing, let's say if we fix M2 and then change position of mirror M1 by even quarter of the wavelength of this laser radiation, we will see changes in the interference picture, because the length L1 will change with respect to L2, and that means the difference in path will be different from initial condition. So that allows to measure this distance with a very high accuracy, higher than any other techniques which are technically available. So one of the practical application of such interferometer, like Microsome interferometer, became very popular recently, and recently was awarded a Nobel Prize for the detection of gravitational waves. The idea there of the experimental technique for the detection of gravitational waves is actually based on this Microsome interferometer, but this lens, the technical challenge and the main problem of realization of this experiment was the requirement of this lens L1 and L2 to be more than 1 kilometer. So as long as possible in order to be able to measure very tiny changes in the length of these channels. So when some event happens in space, like merging of two black holes or two neutron holes, there is some disturbance of the space-time fabric, and this so-called gravitational wave is formed in the space which spreads with the speed of light in all directions. So it was predicted theoretically by Einstein a long time ago. However, our instruments were not capable of detecting these gravitational waves until recently. And because of these advanced experimental setups based on Michelosen's interferometer with very huge, like long channels, like these distances between beam splitter and mirrors M and 2, when this gravitational wave is approaching to the Earth, so it changes the space around it because it affects on the space. And this change in the space could be detected by the change of the length of this distance between beam splitter and mirror M1 and mirror M2. So it comes from certain direction. Let's say it affects this channel along mirror M1 and beam splitter with respect to the other channel M2 and beam splitter. So this tiny change of the length caused by gravitational wave could be detected only if the original length distance between beam splitter and M1 is very large. The larger distance, the larger effect of this gravitational wave, and then the absolute change of the length will be large. So that's why it is quite difficult to realize. It should be all under vacuum condition, all these huge, very long channels, these mirrors, M1 and M2, and the beam splitter and light source and detector, they all should be very well damped, so should be fixed on some very efficient dampers, which will prevent any tiny oscillations of these systems because of all other processes on Earth, or because even driving a car in the vicinity of such instrument could cause some tiny oscillations, and that would result in change of the length, unintentional, and would compromise the experimental data. So that's why technically it was really difficult to realize. However, it has been done based on specifically this Michelson interferometer concept, and was possible to detect gravitational waves. So it became one of the additional ways of exploring space around us, which was not available for us previously. And that is possible because of employing of wave nature of light, in particular this interference effect. Okay, that's pretty much everything what I wanted to say. Thank you very much for attention. If you have any questions, you are welcome. And we will continue our study of wave optics. So which topic will the final exam will be covered by final exam? Final exam will cover all topics, so there will be problems for all topics covered by our course, starting from electricity, like electrostatic field, and finishing with the diffraction of light. So that is actually our next topic. We will deal with this on Friday and continue next week also. Okay, then hope to see you on Friday. Take care and have a good evening. Bye-bye.